We introduced WildFusion, a multimodal implicit neural representations for 3D scene reconstruction in unstructured, in the wild environments. Navigating unstructured environments, such as dense forests, presents significant challenges. In these settings, thick foliage, occlusions, and heavy shadowing often result in sparse or incomplete information. Dynamic lighting and overexposure can make visual sensing unreliable. Traditional LiDAR-based methods can struggle to distinguish objects in cluttered environments. This is why explicit mapping techniques that rely heavily on visual and geometric data usually struggle in dense forests. The complexity of such terrains makes it difficult to generate continuous, gap-free maps, leading to unreliable navigation predictions and increasing the risk during traversal through these environments. We present WildFusion, a novel approach designed to address these challenges by integrating contact surface vibrations with colored point clouds within an implicit neural representation framework. Different terrains will produce different sounds when stepped on, thus complementing the visual signals. By querying specific points in the environment, our model generates continuous 3D geometry and predicts other essential outputs such as terrain traversability, color, and semantic labels for each queried point. These predictions enable downstream tasks, such as content-aware path planning, allowing the robot to adapt and navigate safely through in the wild environments. To gather real-world data, we equipped a quadruped robot with contact microphones to detect ground vibrations and assess surface properties, while proprioception sensors track the robot's direct interaction with the terrain. LiDAR provides precise depth measurements for accurate SDF calculations, and RGB cameras capture color and texture data for terrain recognition. We collect multimodal data across approximately 750 meters of diverse terrain within Eno State Park. The final dataset consists of 550 frames covering 11 distinct terrain classes. This enables pixel-level, information-rich 3D reconstruction and precise terrain traversability predictions. Our model accurately predicts geometry, color, and semantics for previously visited locations from unseen viewpoints, while also generating meaningful predictions in entirely new environments. We performed real-world demo against baseline methods in different scenarios. Elevation-based methods struggle to distinguish between different terrain types, often failing to select the most navigable path. In contrast, our approach actively avoids challenging terrain. Additionally, elevation-based methods misclassify high vegetation as obstacles, causing the robot to stop, while our approach allows it to reach the target. A purely semantic-based approach struggles to differentiate visually similar terrains. However, our method can handle these cases and provide more accurate distinctions. Additionally, we better guide the robot to traverse smoother, flatter areas within the same terrain type for safer navigation. WildFusion enhances 3D mapping and navigation in complex terrains. Its modular design offers potential for future improvements, such as integrating new sensors and boosting real-time performance for even greater adaptability. For open-source codebase and hardware setup, please visit our project website.